Okay, good morning, everybody. A couple of announcements before we begin today. We've got an exam, as everybody knows, next Monday morning at this time. So this is the 10th. And so we've got a number of review sessions and changes in office hours this week to accommodate the exam. We will have review sessions on Thursday and on Saturday. The exact time, place will be announced as soon as I hear from the TAs. So hopefully today or tomorrow we'll know exactly where those will happen and when those will happen. My office hours are going to be changed this week. My Wednesday office hour will be held as normal. Thursday office hour is canceled. And instead, I'll have 2 hours of office hours on Friday. So Friday from 2 to 4 p.m., I will be available and office hours will be held in my office. Okay? If you need additional office hours, you can't make the existing office hours, you can try to set some appointments up with the TAs or with myself. Okay? So just email us and let us know. So, okay, any questions about exam stuff before we get going? Okay. All right. What we're going to do today is talk about semiconductors and one of the basic building blocks of the semiconductor device, which is called the p-n junction. And we ended up last time basically on this slide talking about the fundamental differences between three different classes of solids, okay, according to their electronic structure, and as to how they conduct or whether they conduct electricity well. We have metals on one side, we have insulators on the other, solids that don't conduct electricity, and in between we have semiconductors. And what we said the fundamental difference between these are is that the metals have a partially filled band. Okay? Remember that we're generating bands because we have huge numbers of atoms that are interacting. We're generating molecular orbital diagrams in which the energy levels are very, very closely spaced to one another, and so we generate what are called bands instead of isolated energy levels. If we have a band that's partially filled, we're going to have a metal. That's because there are available states right next to the filled states in gray, the available states, the open states that are uncolored here. And so if you apply an electric field or some thermal energy or something like this, some stimulus, you're going to be able to promote electrons just a little bit above into those empty orbitals, and they'll be able to move, okay, in response to, say, an applied electric field. In contrast, if you do that same sort of thing with an insulator has a filled band, which we call the valence band, and an empty band, which we call the conduction band. And there's a large gap in energy between those two bands. And so an insulator is insulating because these filled bands here are electrically inert. Okay? Because of Pauli exclusion principle, when you apply an electric field to one of these filled bands, there's no net flow of current. Okay? There's no net flow of charge. And the gap here is sufficiently large, larger than, say, 4 electron volts, that at normal temperatures, you don't have a substantial number of electrons in the conduction band, and so you have a highly insulating solid. Okay? So diamond, magnesium oxide, aluminum oxide, lots of oxides tend to be insulators. In between, we have the semiconductors. These are the same electronic structure as the insulators, except the band gap is smaller. And because the band gap is smaller, with thermal energy, we can promote a substantial number of electrons across the gap and into the conduction band, where we can then generate current with the application of an electric field. Okay? So silicon's the most important example. We'll talk about this today. Germanium is another one. Gallium arsenide, cadmium sulfide. Lots of different semiconductors that are technologically important or scientifically interesting. Okay. One very important concept that we need to understand in order to understand solid-state chemistry and physics, especially as it relates to electronic properties, is the concept of the Fermi level. Okay. The Fermi level, which is called EF, okay, is the chemical potential for electrons in a solid, in a system. In other words, the important thing for us really is that it's the level, the energy level, at which we have 50% probability of occupation of the state. So it's the energy level which can be hypothetical, that is, it may not relate to an actual energy level in the solid, in which the probability of electron occupancy in that particular level is 50%. Okay, so let's look at the Fermi level for metals and for insulators and or semiconductors. For a metal, we have a Fermi level that lies right at the interface between the filled and the unfilled states. Right, there's a very large density of states here. We have filled density of states. We have empty density of states. And so the level at which the probability is 50% occupation has to be right at this interface here. Below that, the probability of occupation is near 100%, and above that, it's near 0%. And so this is our Fermi level for a metal. Right? It cuts right through one of the bands. That's another way of describing a metal. It's a material in which the Fermi level cuts through a band and not a band gap. Okay? An insulator is a little bit different, right? We have filled states and we have empty density of states here. And so the place where you have 50% probability of occupation has to be somewhere within the band gap, because these are all filled, these are all empty, and so the transition happens somewhere in the band gap. And it just so happens that it tends to occur right in the middle of the band gap if the density of states of the valence and the conduction bands are kind of equal. Okay? And so that's what I have painted in here. The Fermi level cuts right through the middle of the gap, and that defines an insulator or a semiconductor that's fairly pure at low enough temperatures. We're going to need this concept of the Fermi level, the chemical potential for electrons. In other words, the energy that it takes to add an electron to the system or to take an electron out of the system is another way to think of it, in order to understand p-n junctions when we move forward in discussing semiconductors here. We also needed to understand doping, okay, which we'll talk about in one minute. Okay, let's consider a pure semiconductor. Just think about silicon. It's in the diamond lattice, remember the diamond crystal structure. So all the silicons are tetrahedrally coordinated. You can think of them as sp3 hybridized if you'd like to. Right? If we're sitting at 0 degrees Kelvin, okay, we have this kind of electron occupancy. The valence band is totally filled, and there are 0 electrons in the conduction band. But when we're not at 0 Kelvin, when we're at some finite temperature, let's say room temperature, we're going to have enough thermal energy that some of these valence electrons are going to be promoted into the conduction band. Okay? And in fact, any kind of stimulus, whether it's heat or light or something else, okay, can lead to the promotion of electrons across the band gap, giving us mobile electrons here, okay, negative charges that can move, and very interestingly, mobile positive charges that are left behind in the valence band, empty states where electrons used to be, are formally positive charges, and those empty states can move around with the application of a field too. We call those empty states holes. And so this is a unique idea in semiconductor physics and solid state chemistry, where we have not just electrons moving, but we also have the absence of electrons moving. In other words, we have holes moving too. And the current that's produced in a device is the combination of the electron and the hole current. So this is at 0 Kelvin. We don't have any electrons promoted. At room temperature, we have something like this. A sliver of the electrons at the top of the valence band, right at the top of the HOMO, get promoted across the gap, and they sit at the bottom of the LUMO levels. Okay? These electrons here are mobile, and these holes, these absences of electrons here, are also mobile. Okay? If we apply a field, the electrons move against the field, and the holes move with the field. The current from those two sum up. So if we had equal numbers of electrons and holes and they moved equally well in the field, we'd have twice the current if we consider both the electrons and the holes than if we just consider the electrons. Okay, and so this is the normal condition, of course, when we have a room temperature piece of semiconductor. There's some number of electrons that make it across the gap, okay, and we then get some amount of current. If this was the full story with semiconductors, it would be pretty boring. Okay? Because all we would be able to do is to change the temperature, for example, or change the semiconductor material that we're using. And we could then change the number of carriers that we have in the conduction in the valence band. But we can do a very interesting tweak to semiconductors to independently tune the amount of electrons that we have and the amount of holes that we have. And so we can really massively increase the conductivity of a semiconductor if we choose to. And the process that we use to do this is called doping. Okay? What we're going to do is we're going to understand doping in terms of one important semiconductor, silicon. There are, as I mentioned, many different kinds of semiconductors. And this is just a small list of some important ones, in order of decreasing band gap, essentially here. Okay? So titanium dioxide comes in a couple of different crystal structures. But the two most important crystal structures have band gaps that are around 3.0 to 3.2 electron volts. That is in the UV part of the spectrum. And so if you have a piece of titanium dioxide, you have a colorless semiconductor that absorbs light only in the ultraviolet part of the spectrum and higher energies. Okay? Titania is an extremely important material in lots of different areas, as mundane as, say, paints. So titania is found in lots of different paints. And as kind of high-tech as trying to do water splitting and generate hydrogen from sunlight. Okay? So it's a very well-studied material. Some other semiconductors in decreasing band gap, cadmium sulfide has a band gap of 2.4 electron volts, and if you can convert that to wavelength, you'd realize that it absorbs blue light, and so it's going to look yellow. Okay? Mercury sulfide, this is called cinnabar, 2.1, that's a red band gap material, so it absorbs green and blue light, so it looks red. And then you get into materials that have smaller band gaps that get into the infrared part of the spectrum. Cadmium telluride looks black. Silicon, the one that we're going to focus on, a band gap of 1.11 or 1.12 electron volts, looks dark gray. Okay? It absorbs all of the visible photons, but it actually reflects a lot of light too, and so it has a kind of a gray metallic luster to it. Germanium looks a little lighter gray than that. Silicon is, as it so happens, the purest material on the planet. Okay? So silicon can be made because there's been such a huge investment by Intel and other companies, right, to make very, very high performance transistors for computers. Silicon can be made more pure than any other material on Earth. And these are examples here of two different silicon wafers, okay, that integrated circuits are built on. This is a 12-inch wafer, and this is the new generation of 18-inch wafers. Right? My group uses a lot of silicon wafers in our research, and we use little baby 4-inch wafers. So these wafers here are actually quite astonishing. They are single crystals all the way across, and they are pure to like 1 part in 1 trillion or better. So there's pretty much only silicon atoms present in there. A little bit of oxygen, a little bit of carbon, and that's about it. Okay? So let's talk about silicon. One of the important things that you need to be able to do with any semiconductor is control the conductivity. Okay? And the way that we do that is by the process that we call doping. Okay? So how does doping work? Doping, first of all, means that we intentionally add an impurity element into the semiconductor lattice. Okay? So we have silicon. We replace one of those silicons with another atom, okay, that has a different valence electron number. When we do that, our goal is to change the electronic properties, to change the conductivity, to change how fast the electrons move, perhaps, and other things that we might be interested in adjusting. So let's look at silicon. Silicon has, of course, 4 valence electrons. We have the valence band filled, we have the Fermi level in the middle of the band gap, and we have an empty conduction band. Let's just use kind of low temperatures here to just simplify the diagrams. At reasonable temperatures, we have an equal number of electrons and holes that will be present in this material, because in order for an electron to conduct, it has to be promoted across the band gap, and so it leaves behind a hole. So the number of holes and the number of electrons are equivalent in an undoped or pure semiconductor. Okay? But also, the conductivity is low, okay, because we're relying only on thermal energy to promote electrons all the way across this band gap, which is fairly large. 1.1 electron volts is many, many times thermal energy. And so the number of electrons that make it across is actually fairly small. What happens if we take a silicon atom with 4 valence electrons and we replace it with something that has 5 valence electrons? For example, if we add a phosphorus atom where a silicon atom sits in the crystal structure. Phosphorus has 5 valence electrons. And what ends up happening is that the phosphorus makes bonds to its 4 neighboring silicons with 4 of its valence electrons. The 5th valence electron it has, it can donate to the conduction band. Okay? It's very weakly held, and with a little bit of thermal energy, the phosphorus will release that 5th valence electron into the conduction band. The way that we show that in an energy diagram like this is that when phosphorus is added to the crystal structure, it generates electron states, filled states, that exist fairly close to the conduction band edge, okay? The bottom part of the conduction band. And at normal temperatures, what happens is that a lot of the electrons that are held, those 5th electrons that are held by phosphorus, have enough thermal energy to get promoted into the conduction band. And so at equilibrium, what we have is a situation where we have lots of free electrons, and we have very, very few free holes. In other words, the material is dominated by electrons, negative carriers, and so we call this kind of semiconductor an N-type semiconductor, because it's negative, or the conduction particles have negative charge. These states here, because phosphorus comes in with an extra electron to donate to the lattice, are called donor levels, right? So that fifth valence electron is donated to the semiconductor, so we call these donor states. Okay. One last thing to note here is that the Fermi level has moved up when we add these donor states, when we N-type dope the semiconductor. And it must do that, right? Because if we add a bunch of filled states in here, the position that's half filled, where we expect 50% probability, has to be above that, right? So it's going to be between the level of the phosphorus impurities and the edge of the conduction band. And so we get the Fermi level moving quite close to the conduction band edge. That's a way that we can immediately tell that a material is N-type, is that the Fermi level is closer to the conduction band edge than it is to the valence band edge. What if we go the other way? We could, instead of substituting silicon with a phosphorus or something else that has 5 electrons, we could substitute with something that has 3 valence electrons, 1 fewer valence electrons than silicon. If we do that, let's say we add boron. Okay, boron is a group 3 element, has 3 valence electrons. What happens is that boron sits on a silicon site, but it doesn't have enough electrons to bond to all its silicon partners. It has 3 electrons, so it bonds to 3 silicons, but it has 1 empty bond. That empty bond is essentially an attractive force for electrons that are nearby. And you can actually trap electrons onto that site that's generated by the boron. This level is called an acceptor level, okay, because it can accept electrons from the lattice. And typically, acceptor levels occur very, very close to the valence band edge. And so what happens is you come in, boron generates a bunch of empty acceptor levels that are available to accept electrons. And thermal energy allows some of the valence electrons to be promoted into those acceptor levels. And the net result is that at thermal equilibrium, what you have is a plethora, an excess of holes. Okay? You've trapped some of the electrons here. You've generated empty states, which are free to move in the field. And we have a p-type, a positive dominated semiconductor, p-type semiconductor. Just as with the n-type semiconductor, the Fermi level goes up. Here, the Fermi level goes down. Okay? The Fermi level has to sit between the levels that are highly populated and those that were unpopulated. This is the 50% cutoff. Okay? So the Fermi level close to the valence band edge indicates we have a p-type semiconductor. Close to the conduction band edge indicates we have an n-type semiconductor. Okay? Okay. Here's another picture that helps you understand a little bit more. Okay? This is saying exactly the same thing. Okay? If we put in group 5 or group 3 elements, we can n-type or we can p-type dope. Here's the reason for it. Silicon has 4 valence electrons. These elements have 5. These elements have 3. And so if we put in one of the 5 elements like antimony, here we have 4 electrons to bond to the silicons. We have another electron that escapes into the lattice, into the conduction band. Whereas if we have boron, it has 3 valence electrons to bond to 3 of its nearest neighbors, but it lacks an electron to bond to the 4th, and so this hole here acts as an acceptor state, and an electron can fall into there. And that's what happens when we generate a p-type semiconductor. These diagrams here are exactly the same that I showed before, okay, just to show it all on one slide. So we would say that this is an n-type material because the Fermi level is close to the conduction band. This is p-type because it's close to the valence band. The n-type materials are dominated by donors, and the majority carriers are electrons. The dopant type is an acceptor for a p-type material, and it's dominated by holes. Okay? Yeah?
On the previous slide, you had circles, and with the boron one, you have 2 filled circles, and phosphorus, you have 3 filled circles.
Purely schematic, yeah. I should have drawn 6 instead and just filled them halfway up. Yeah. So the amount of filling depends on the energy distance, the gap between these states in the valence band, and the gap between these states in the conduction band, the temperature, and other things. So this picture here is just very simplistic and schematic in nature. Yeah. The take-homes are basically that you have an excess of electrons in this case, you have an excess of holes in this case, and where those donor and acceptor states lie and the Fermi level lies are approximately correct. Okay. Other questions? Yeah.
In regards to this doping, is there an influence as whether this is a metal, non-metal, or metalloid as well?
It does, yeah. So what we've shown here, the simplest situation, an elemental semiconductor doped by a group 5 or group 3, just one valence electron different. The reality is a lot more complex if you start looking at other possible dopants. You can have dopants that introduce multiple states, states that are in the middle of the band gap. There's many different possibilities. And so we've shown just kind of the very basic classical picture to understanding doping. Yeah, it's a very messy world out there, it turns out. Yeah. But this is what Intel and other companies that make semiconductor devices are using. They add boron, they add phosphorus to their silicon. Okay? Questions, other questions? Okay. Okay. One of the key building blocks of semiconductor devices that can generate lots of cool devices, including things like transistors, solar cells, photodetectors, light-emitting diodes, and laser diodes, are based on just layering a p-type material and an n-type material together to create a p-n junction. Right? Just a layer of p-type material and a layer of n-type material, usually with some other stuff around it, electrodes and other things. But the basic building block is just putting these two materials together. So let's try to understand in a qualitative way the physics of the p-n junction and how it might apply to some of these different devices that are ubiquitous, right? Including in my laser pointer, in all of your computers and all your gear, right? These devices are everywhere. Okay, so what we're going to do is we're going to consider the so-called band diagram or the energy diagram of a p-n junction, and we're going to build it from sort of basic principles here. So let's consider what happens if we take a p-type semiconductor, let's just call it silicon, and an n-type semiconductor, also silicon, and we make a junction. We put them together. We slap them together. Okay? Before we do anything, when they're held off from each other, before they touch, we have energy diagrams that look like this. For the p-type material, the Fermi level is deep. For the n-type material, the Fermi level is shallow. Okay? When we make contact between these two materials, we have an excess of electrons here and we have an excess of holes here. So when we put them in contact like this, the electrons, which are in high concentration on this side of the junction, are going to, by diffusion, move to the left. Okay? They're going to move from the n-type material into the p-type material. Diffusion of holes will also happen. Holes are in excess here. There are very few holes on this side, and so holes by diffusion are going to move to the right. Okay? As this process happens, as this diffusion process happens in the initial nanosecond when they touch, okay, what happens is that as these electrons move to the left, they leave behind positive charges, ions, those phosphorus impurities, on the right-hand side of the junction. And the holes that go this way leave behind negative impurities, the boron, on the other side. Okay? And that process continues, this diffusion process continues until the electric field that's built up by the ions that are left behind counteracts the diffusion process. And we achieve a balance. Okay? The diffusion continues, and there's a net current until the electric field that's generated by the ions that are left behind stops that diffusion current from continuing to increase. And what ends up happening then is we have a balance between diffusion on one side and an electric field-driven process of the carriers in the reverse direction. Okay? And this electric field-driven process is called drift. Okay? Drift is the name that we assign to a current that's generated by an electric field. You say that the electrons or the holes drift in the field. Okay? And so this will happen until we achieve a balance. And that balance can otherwise be described as when the chemical potentials on both sides of the junction, okay, on the p-type side and the n-type side, are the same. Okay? The chemical potentials are the same when the Fermi level, it's just another way of saying it, when the Fermi level is the same throughout the entire device. Okay? And so we go from the initial position where the Fermi level is below this Fermi level on this side, and at equilibrium, we have the Fermi levels aligning like this. In order to align the Fermi levels, you see that we have an energy offset here between the two sides of the junction. Okay? This offset exists because of the ions that are left behind, the positively charged ions on the right-hand side of the junction, on the n-type side, and the negatively charged ions on the p-type side that are left behind. This creates an electric field, okay, because you have charge separation across this junction. An electric field, by necessity, is the gradient in the potential energy. Right? So the electric field in this case goes from the positive to the negative side like this. Okay? So anytime you see a change in the potential energy, you can guess that there's going to be charge separation across that change. Okay? Charge separation is creating an electric field, which in other words is a gradient in the potential energy. These are all the same ways of saying the same thing, different ways of saying the same thing. Okay? And so at equilibrium, okay, equilibrium meaning just at normal temperature without additional light or anything else, no electric bias attached to the device, we have a situation that looks like this. Okay? We have an energy offset. This creates an energy barrier for electrons moving from the n-type to the p-type side. So the electrons that are in the conduction band have to go up this hill to get up here. And the holes that are on this side have to go up this hill to get to the valence band on the n-type side. Okay? So we have an energy barrier, we have an electric field. This is called a built-in field or built-in potential energy. Okay? It occurs spontaneously when we make a p-n junction. And it's the key thing to understanding the p-n junction physics.
I'm not quite sure if I'm understanding how this is working, because the n-type is the donor and the p-type is the acceptor in this case.
That's right.
Would there be a lower energy difference as a consequence of it?
Should be a lower energy difference.
I mean, we see that it's kind of like the energy level that's going up on a slope up towards, right, in that case.
Yep.
It wouldn't be.
So the determining principle here, the way that we can always understand how to build an energy diagram like this, is just that at equilibrium, the Fermi levels have to line up. And so the way I've drawn it here is I've just shifted the p-type material up. You can see between here and here. I just shift the p-type material up, right? You could equivalently shift the n-type material down if you wanted to. But you have to find a way to line up these two Fermi levels on both sides. Right? What really happens is that you have some motion on both sides of the junction. But that's a little bit more difficult to see if you just have a simple set of slides like this. Right? I'm just trying to emphasize that we need to line up the Fermi level to make equilibrium. Okay. So let's see what this tells us, okay, why this is interesting. This is another picture here, okay, of the same junction, okay, showing what's really happening in equilibrium. Remember, like any equilibrium, any chemical equilibrium, this is a dynamic situation. We have counterbalancing currents. It's not that the currents are zero, it's that the net current is zero. Okay? And it so happens that both for the electrons and for the holes, we have two types of currents. We have that diffusion current that I was talking about that continues to exist because we have a concentration gradient from one side of the junction to the other. That's the diffusion current that drives electrons from the n-type to the p-type, and diffusion that drives the holes from the p-type to the n-type. Okay? The other current that we have that balances out that diffusion current is the drift current. Electrons that are up here get pulled by the field across the junction and into the n-type. Right? Holes that are here get pulled by the field this direction. And at equilibrium, there's no net current. What that means is that this drift and diffusion current are exactly balanced, and the whole drift and diffusion current are exactly balanced at equilibrium. Okay? What we're going to do is use this energy picture and apply voltages to the p-n junction to knock this thing out of equilibrium. And what we'll see is very interesting behavior of the current when we apply different voltages. Okay? And it's this behavior that allows us to use these devices for transistors and for other kinds of technologies. Okay? Just remember that we always have diffusion and drift currents for both the electrons and the holes happening. Okay, let's look at the current voltage characteristics of one of these p-n junctions. A p-n junction is also called a diode, a semiconductor diode. And a diode is something that passes current strongly only in one direction. And in the reverse direction, doesn't pass much current at all. Ideally, doesn't pass any current at all. Okay? So this is unlike a resistor. A normal resistor, if you apply a positive voltage, it conducts a certain amount of electricity. If you apply a negative voltage, it conducts the same amount in the reverse direction. Right? Here, we're not going to find that. It's going to be quite different in the forward and the reverse direction. So let's look. Okay, here is our current versus voltage curve. At equilibrium, we have no current and we have no applied voltage, so it passes through the origin of those axes. Okay? And this is, I'm showing here the equilibrium situation. Okay? No net current. Let's now apply a positive voltage to the p-type side of the diode. And this is the convention. We always apply the voltage to the p-type. Okay? If we apply a positive voltage to the p-type side, what happens? Well, it drives the p-type down in energy. So both of the bands and the Fermi level shifts down. Okay? We're applying a positive voltage. That means that electrons there are attracted, more attracted to that side, and so they're lower down in energy. Okay? What happens to the energy barrier when we go from, from equilibrium to forward bias, positive bias on the p-type side? The energy barrier gets smaller. As the energy barrier gets smaller, that means that the barrier for diffusion of electrons from this side to that side is smaller, and the barrier for diffusion of holes from this side to that side is smaller. And so when we apply a positive bias, we get a very strongly increasing current. And it turns out to be an exponential function of the voltage. So as we go into forward bias, we get an exponentially increasing current in forward bias, because this barrier to diffusion becomes smaller and smaller and smaller. And the escape probability is exponentially dependent on the barrier height, it turns out. Okay? So we have an exponential increase in current in forward bias. What happens if we apply a reverse bias, negative bias to the p-type side? That's going to do the opposite. It's going to increase the barrier height. Okay? The barrier height is now quite a lot larger. Okay? That makes it that much more difficult for electrons to fuse up and into the p-type side, and the same thing for holes. And it basically shuts the diffusion current down. Okay? The diffusion current essentially goes to 0. And so when you go into reverse bias, you find that you have a very, very small negative current that's just from the drift component. Okay? But we have, in an ideal diode, essentially 0 current in this direction and an exponential current in the opposite direction. And it's because of this barrier that exists, okay? This asymmetric barrier that exists in the device. So we have a diode. We have something that conducts very poorly in one direction, something that conducts very well in the opposite direction. And this is the key functionality of the PN junction that allows one to build memory, logic elements, transistors for displays, and then solar cells and other things. Okay, let's talk about some of these classes of devices that one can build. We're going to focus on so-called optoelectronic devices. Those devices that include an optical component and an electronic component in their function. So we're going to focus on solar cells, photodiodes. Photodiodes are just light detectors, high-tech light detectors. And then light-emitting diodes, everybody knows the LED, right? And laser diodes. Laser diodes are kind of a modification of the LED to get lasing action out of the material. This general diode behavior here, we can understand how the solar cell, photodiodes, et cetera, function because they just operate in different regions of the current voltage curve here. You probably know that in a Cartesian set of coordinates, this is the first quadrant, this is the second quadrant, this is the third quadrant, and this is the fourth quadrant. Okay? If we operate the device in the fourth quadrant, we have a solar cell. We'll talk about this one first. Okay? If we operate a device in the third quadrant at negative bias, we have a photodiode or a photodetector. And if we operate the diode in the other possibility, the first quadrant, positive bias up here, we have either a light-emitting diode or a laser diode, depending on how the device is actually constructed. We don't have any operation in the second quadrant because the current voltage characteristics never pass through the second quadrant. It's only the fourth, the third, or the first quadrant. So let's look first at the operation of a solar cell. Then we're going to go on to the very, very similar photodiode. And we'll finish up with the discussion of the light-emitting diode and the laser diode. Okay, so first of all, the solar cell. What does a solar cell do, right? It takes sunlight, or light in general, and it converts it to a current and a voltage. It converts it to electricity. And so solar cells, of course, are the panels that you see all over UCI and increasingly in Southern California. Slow to take off, but it's happening. And most of it's made out of silicon. Okay, there's a couple other technologies, but most of it's silicon technology. And so what we're going to talk about is directly applicable to understanding how those devices work. Here's our current voltage characteristic that we showed before, the diode characteristic. Okay. What happens in a solar cell? It's just an illuminated diode. Okay, we're just shining light on the diode. When we shine light on the diode, what happens to it is that the current voltage curve shifts down. Ideally, it just is a rigid shift down, and there's no change in the curve. There's no change in the shape at all. Okay? So when we illuminate it, we get under the light, we get this red IV characteristic. And what you can see that's quite interesting here is that under the light, with no applied voltages or anything, we have a photocurrent. Okay, this is a current that's due to the application of photons, so we call it a photocurrent. This is the current axis here, and so we have a certain amount of current that happens with no applied voltage. Okay, so spontaneously the material generates current when it's illuminated. It also has a voltage that's associated with it. We call this the photo-produced voltage, or the photovoltage. And the voltage is the voltage that, or the value here that crosses the voltage axis. No current flowing, we generate a pure voltage at that particular point. Okay? And this is important, right? You want to generate both a voltage and a current if you're going to produce power from shining light on a semiconductor. Okay? Power, remember, power is equal to current times voltage. So you have to have both. And so typically a solar cell is operated right in this region here, where you have both a current and you have a voltage. Okay? Let's understand how it actually goes down. Okay? So here is our energy profile for the PN junction that we've already shown. Okay? And what we're going to do is we just are going to illuminate it. When we illuminate it, what happens is that photons are absorbed all throughout the semiconductor. Okay? And those photons cause promotion of electrons across the energy gap and into the conduction band. And so both on the p-type and the n-type side, in principle, we generate free electrons and we generate free holes. Okay? So we're doing that down here, and we're doing that down here. We now have an overabundance of electrons on the p-type side and an overabundance of holes on the n-type side. And any electrons here that get close to this field are going to be swept across the junction. Okay? And you're going to generate a current of electrons from this direction to this direction, downhill, and a current of holes downhill from the n-type side to the p-type side. Okay? So there's a current that's generated because of the application of the light. And there's also a voltage associated with this. The voltage is due to this built-in potential energy difference here. Okay? So those carriers are going to come out with a voltage that's related to the size of that barrier. And so you'll have both a current and a voltage, and that's how you get this kind of current voltage characteristic here. If we then apply this, we kind of wire up this solar cell with something like a light bulb, we can power the light bulb. Right? It produces a DC current, low voltage. By stringing lots of solar cells together, we can manipulate the voltage, right? By stringing them in series and in parallel. You probably remember from basic physics. And so we can generate pretty much any DC current and any voltage that we want to. Okay? And then the way it's typically done is if you put this on your roof, you usually use AC power for all the stuff in your house. And so you have to take the DC power that's produced by the solar cells and put it through something called an inverter, which inverts the DC to AC electricity. Okay? And then you can use it to power your microwave and TV and everything else. Okay? So that's the basic operation of a solar cell. Any questions about how this works? There's, of course, a huge amount of extremely interesting chemistry and physics that go into this.
So you said that it's working only in the fourth quadrant, right? So I guess the line on the, what is the line on the first quadrant?
Yeah, so I said before that the solar cell operates in the fourth quadrant, which is this quadrant of the Cartesian axes here. And that, what I mean by that is that when we actually operate a solar cell, we're going to choose a resistance across it that allows us to operate right in here and pretty much right in the middle, so that we have the maximum voltage and at the simultaneous time the maximum current that we can achieve from the device. This is also called the power producing region. Okay? If we operate up here, then we have to add a bias to get to that position. We have to add voltage. And so we're not any longer generating power. We're actually consuming power. Right? And so the solar cell is the only of the devices that will show that operates without the application of some sort of voltage. Okay? It produces its own voltage. Okay, let's look next at a photodiode. Okay? A photodiode is a light detector, like I mentioned. It's exactly the same thing as a solar cell, except instead of operating the solar cell in the power producing region, we operate the solar cell in reverse bias. We apply a reverse bias to the diode, and we shine light on it. And the whole function is to detect that light as a current, okay? So that we can sensitively detect photons. So this is what a photodiode looks like. PN junctions held in reverse bias, used to detect light. We have the same sort of IV that we just showed for a solar cell. Okay, we illuminate the photodiode. Okay, it could be made out of silicon. These are some photodiodes. This is kind of back in the day photodiode. This is more modern photodiodes out of silicon. Here's a photodiode that's made from germanium. Okay. You can see in each of these cases there's 2 wires that go in. That's because we have 1 wire attached to the p-type and 1 wire attached to the n-type side of the device. Right? Photodiodes can be operated in the visible part of the spectrum. Okay, that's the most typical. But also photodiodes are useful for looking at long wavelength radiation. Right? So you can make an array of photodiodes and you can make a detector for infrared, for heat. Right? So these are infrared detectors that are used by the military, right? Police and so forth. That's how these are made, right? Arrays of photodiodes. Okay, so how does it actually work? We apply a negative bias to the diode with a battery, right? We apply the negative voltage of the battery to the p-type side. That drives the barrier higher in energy. The important thing here is that when we add this negative bias to the p-type side, when it's in reverse bias, the spatial extent of the electric field is much, much larger. Okay, so the thickness of the region where the electric field extends increases as we go more and more reverse bias. And that has 2 important functions for the photodiode. First of all, it increases the region in which if a photon is absorbed, where's my photons? There. If a photon is absorbed, these carriers get swept across the junction and collected as a current. Okay, so it increases the volume in which that happens in the semiconductor. Okay. So that increases the sensitivity of the diode to light, which is important. The other thing it does is we can't totally explain this in this class, is that it increases the speed of the photodetection. So we can very rapidly respond to changing light, right? So this might be important in lots of different things, especially in science, right? If you want to be able to detect light quickly because you have some sort of event that you're trying to monitor, you use a photodiode. You increase the distance between the positive and the negative side. That decreases the capacitance and allows you to detect light more quickly. Okay? So it improves the speed. So we've got our solar cell, we've got our photodiode. Okay? One of the last things that we want to talk about, unless there's any questions about the first 2. Questions? Okay. The last one that we want to talk about is the LED laser diode. Okay. So the solar cell operates in the 4th quadrant. The photodiode operates in the 3rd quadrant when we apply a negative bias. The other possibility for the diode characteristic is that we operate in the 1st quadrant. We apply a positive bias, not a negative bias, but a positive bias. Okay. Why would we want to do that? Well, the solar cell takes light and generates current, right? We can reverse that process. We can take current and we can generate light from the same kind of device. Okay? And that's what we do when we put the device in positive bias. We flood the device with lots and lots of current. And if we've constructed the device appropriately, a lot of the electrons and holes that enter the device will meet each other near the middle at the p-n junction, and they will recombine, it's called. The electrons will find the holes and fall down into the holes, and they will emit light as this process. Okay? That light emission is what you see when you turn an LED on, right? Or when you turn a laser like this one on. Okay? So what happens is we put the positive terminal of the battery on the p-type side. That lowers the barrier, okay? And we drive a ton of current from this side. This wire, the electrons travel this way, and from this wire, the holes travel this way. Lots of current enters the device. And when the electrons and the holes meet up, lots of them fall down into the empty states, and they emit light as part of that process. If we have just sort of a simple device, I mean, it's simple in a way, but it's still incredibly complicated, long road to technological maturity. You have something called an LED. Okay? You have light emission, and you put the device, there's a little semiconductor chip in there. You put the device in a dome whose job it is to kind of diffuse and direct the light outwards. Okay? And so you get this very nice kind of halo, glow of light. It can be very, very bright because this process can be very efficient. Okay? And so you can have something like 5% maybe, or even larger percentage of the electrons and holes that meet each other recombine and emit light. Okay? That's pretty good. Okay? You can make all different colors. Okay? The colors are made by selecting different kinds of semiconductors. Silicon is not used for this process. Silicon is actually a very poor light emitter. So what's normally used are things like gallium arsenide, gallium nitride. So gallium arsenide makes red light and infrared light. Gallium nitride makes blue light. There's other combinations and lots of different structures that can make the whole rainbow. Okay? It's easier to make some colors than others, and so you'll find these days, for example, making a green LED is a real problem. Making a really efficient green LED is a problem. And still making very efficient white LEDs for like indoor lighting, which is the main application for LEDs, kind of solid-state lighting applications, is also not a solved problem yet. Okay? So there's a lot of additional research that goes into trying to make more efficient LEDs. The other way that you can do it is you can slightly change the geometry, and you can make a laser with this approach. What a laser requires is a much better optical cavity, and you need something called population inversion. So you need to have a slightly different setup, but the idea is the same. The light is emitted. In a laser diode, it's emitted in a certain direction, very nice collinear beam, collimated beam, so I can make a nice spot on the wall like that. That's because this is something called a vertical cavity surface emitting laser that emits light in a certain direction. Okay? And again, you can use different materials for different colors. So this would be gallium arsenide. This is gallium nitride. The green one is actually not usually an LED, laser diode. It's a mixed technology.
So the Nobel Prize this year in physics was given to the blue LED.
For this.
Why is that such a great feat?
Okay. So first of all, it was extremely challenging. So a whole new materials class had to be developed to make the blue LED, the blue laser diode. This is all based on gallium nitride. So gallium nitride is a material that has a wide band gap, about 3.5 electron volts. So it's kind of in the UV blue region of the spectrum. And basically, it was what people did with silicon in the 1950s is what people just did with gallium nitride in the 1990s and the 2000s. Take a material that was very rich in defects, clean it up, understand its physics, and get it to work properly. Why is it important? Well, it's important for lots of different possible applications, some of them already in existence. So one thing is white lighting. Okay? So you can have indoor lighting that's super energy efficient. Another is information. So like the Blu-ray discs. So you can pack a lot of data on those discs because you use a small wavelength blue laser, right? Purple laser, actually. And that's based on gallium nitride technology. Medical applications, there's lots of different reasons that we want to be able to access all the different colors and control the light emitting properties of the devices that we're making. So in a nutshell, that's why the gallium nitride got it.
Is there a lower limit to the wavelength of?
No, there's not really. So people make very, very deep UV lasers, not using diodes typically, but by using other approaches. But with diodes, with semiconductor devices, there's no reason that you can't go much, much bluer and into the deep UV with these materials. Yeah. Okay. Are there any more questions? Let's finish up then with just a summary slide of Chapter 7. So we showed that crystalline solids possess long-range periodicity, and we can describe them as just translation of a repeating unit that we call the unit cell. Okay. We said that all crystals belong to one of the 14 Bravais lattices, and we can very powerfully describe crystals as close-packed arrays that have a certain number of interstitial sites filled. Okay. So we showed several different crystal structures like that. The structure of ionic crystals, which is what we focused on for part of the lectures, depends on the radius ratios, right? The stoichiometry, whether we have 1 to 1, 1 to 2, 1 to 3, and electronic factors that we didn't really describe a whole lot. We can understand the lattice energy based on Born-Haber cycles, right? Those are thermodynamic cycles, thermochemical cycles. And we have an equation called the Born-Lande equation that we can use to estimate lattice energies. Electronic structure depends on the frontier orbitals, right? These are mixes of lots of different molecular, atomic orbitals making molecular orbitals that go into bands. Okay? These are the same as what we see in the molecular cases. And we showed that junctions between p-type and n-type materials can be used to make a whole different variety of technologies, solar cells, light-emitting diodes, etc. Okay? So this is going to finish up our review of Chapter 7, and next time we'll start on Chapter 6, going back to talking about acid-base chemistry.